This talks about amateur radio and high altitude ballooning in the UK and how I perceive it to be different from that in the US. Now, I have to say perceive because I've never flown in the US, and everything I've learnt about the sort of US high altitude ballooning has really been through um, snooping on GPSL for the last 10 years. Um, but I think I've got a reasonable view of what the major differences are. Before I get into that, though, I thought I'd quickly tell you a bit about myself. Since you've probably never heard of Steve Randall before, I hope I'm reasonably well known in the UK high altitude ballooning community, but I guess in the US nobody will have heard of me. I've been doing amateur radio for 50 years, so you can tell from the wrinkles that I'm no spring chicken. And I got interested in high altitude ballooning way back as a result of doing amateur rocketry, and I was looking to launch a raccoon from a balloon, a rocket from a balloon, and so I started to gain an interest in ballooning, and then sort of got diverted and haven't achieved that raccoon objective. But I guess that's life. I've flown probably around about 200 flights if you include those with other people. So no newbie to high altitude ballooning. I run a small business selling balloons from China and parachutes from the US. UK-US differences. The biggest difference is you're not allowed to use your ham radio license for transmitting from the balloon to the ground. You can use it for other things, such as chase cars. So another big difference, I think, between the UK and the US is limited geography. The country is only about 250 miles wide at its widest point. You're never more than 70 miles from the sea, so it's really easy to make a mistake and land a payload in the sea, or even potentially other countries. So it's essential to have good prediction software to ensure that you don't do that. Also, our population density is quite a lot higher. It's probably something in the region of approaching 10 times higher than the US. And that again means that we've got towns and cities and airports to avoid quite a lot more, I think, in terms of per unit area of the country. Then the final major difference, I think, is the permit requirements. You're required to get a CAA, that's our equivalent of the FAA. You're required to get a permit from them for every single HAB flight, with the exception of something that's defined as a small balloon, and that the definition for that is essentially that the balloon and its equipment it's carrying must all fit within a 2 meter, that's probably around about 6'6", something like that. It's got to fit within that dimension through the course of its entire flight. So it really means you're limited to quite a small balloon. I think you can just about fit if you put the camera or whatever equipment into the neck of the balloon, you can just about fit it into some of the 100-gram balloons. But as it's turned out, actually that was a driver to some of the other developments that we did in the UK. So the UK amateur radio license specifically says the radio equipment may not be established in any aircraft or airborne vehicle. And as we'll come and see later, actually that's even been more defined, but it essentially means you can't use it in a balloon. Now that is true in other European countries. It's not just the UK, but the major countries like France and Germany do allow high altitude balloon flights. So it's a little bit more restricted in France, but I think in Germany certainly they use APRS and tracking. In my dealings with the regulator, their main concern appears to be the potential for interference over a wide area. Although and this is very much a personal view, I get the impression that the air regulator has had some input into this, and I guess the air frequencies aren't that far from 2 meters. So anyway, that's just a bit of a guess on my half. So what did this mean? How did we get over this? It's clear that radio is essential for tracking my balloons, at least in my opinion. So how did we get over not having an amateur radio license and transmissions from a balloon using that? Enter license exempt operation. Yeah, most administrations have these. There are allocations of small bands of frequencies where with using low power, you're allowed to use those frequencies without any license. So in the UK, there are a number of frequencies allowed, but 10 milliwatts on 434 megahertz is allowed, and 25 milliwatts on 868 megahertz, and both of those are reasonably well used now for high altitude ballooning. Fortunately, the 434 megahertz allocation sits right in the middle of the 77's amateur radio band. I suppose from an radio amateur's point of view, maybe that's unfortunate, but from a high altitude ballooning point of view, that's very fortunate, because it meant we could reuse our amateur radio equipment for receiving these transmissions. If you do manufacture some of this type of equipment, I mean, it's used for things like doorbells, key fobs, remote controls, Wi-Fi. So if these type of devices are quite widespread, but if you manufacture them, you need to meet certain set standards, and that in turn has led to the introduction of modules which are sort of like pre-certified to those standards. In the US, I believe this is called Title 47, Part 15, and that defines things that are basically license exempt. Typically, the stuff is transmitted on this is sort of like narrowband, low data rates. Obviously, Wi-Fi is a bit wider, but that's the sort of thing that you'll find this used for. But we found using just these sort of low powers, the line of sight operation is quite commonplace. 500 miles or 600 miles is often achieved. The first few flights we had in the UK didn't use radio tracking at all. They used homebrew network trackers, effectively equivalent to a GPS and mobile phone tracker that you get today. But we found that they didn't track above 1,000 meters. The phone network is not designed for that. So pretty much a quite scary experience. You launch your balloon and you don't hear for it for 3 hours, and then it either phones home and you know where it is, or it doesn't, and you never know where it went. So we did some initial tests with 10 milliwatts on 434 megahertz using same standards really as APRS, and got about 30 miles doing that. I mean, it certainly proved that the tracking capability was there, and we're really impressed by being able to track through the entire flight. But it just didn't have the range really to allow us to confidence, particularly at that time, about being able to keep in touch with the balloon throughout the flight. So we looked at an alternative and found that 300 baud RTTY direct FSK was pretty good. We had a couple of balloons that sort of disappeared out into the North Sea, and we were still hearing them 200 odd miles away. So we thought, yeah, that works for us. So it pretty much just became a de facto standard pretty quickly. Early developments. So leading on from that, we needed a way of receiving those signals and decoding them, and developed a version of FLDigi, which we call DLFLDigi, which stands for Distributed Listener FLDigi. And that's what we use to receive the signals, decode them, and upload them to the Near Space Tracker. And that was an early development too. that was set up like an equivalent of APRS.FI, and it takes in data from all the receiving stations, no matter which type they are, and displays them on a map. You can use APRS. You can set that up and have that come up onto the tracker. You can certainly use the RTTY type of system, and you can also use LoRa and LoRaWAN, and all of those things have got some method of getting the data from the network onto the tracker. Another development early on was the landing predictor. We needed that to get the accuracy. It needed to keep within the UK, and also the burst calculator, which proved quite useful in being able to handle variations in balloons and amounts of fill, etc. By the way, it's certainly not unusual to see that type of track landing in the middle of the North Sea, even this time of year. I've got a couple of slides here really to show the differences between APRS and the habitat system. In essence, as I understand it, on APRS you transmit from the balloon primarily using 2 meters, and the signal might digipeat in order to get to a gateway, but either directly or indirectly the packets get to an iGate, which then sends its data over the internet to APRSIS, which sort of like sits as a repository. Then if you want to see that on the map, you use APRS.FI, which is sort of backends onto APRSIS, and pulls data off and puts it onto a map. In essence, the habitat tracking system isn't vastly different. We use different frequencies and different ways of getting the data there. But I think the key difference is we also use this sort of central database system, habitat in our case, to store SSDV images and could do that for other data as well. So it's a central repository of both the telemetry for the tracking and SSDV pictures. And as I will come to explain in more detail later, SSDV can have the packets can be received by multiple stations and therefore reduce the amount of lost packets in a picture. So it's useful having a central store for all the data. And we've got gateways or interfaces into a number of other sources of data on habitat. We've got AutoRx, which automatically tracks Met Office radiosondes. We've got interfaces to APRS. We can actually pull data off of APRS and put it on the habitat tracker. There's DLFL-Digi, which I've mentioned, and LoRa and LoRaWAN. We've got a gateway for LoRaWAN. And I also believe people pull off Whisper and send it for balloon tracking, send that to Habitat too. So a number of sources of data which all end up as balloons on the Habitat tracker. And I guess my final points here are that Habitat tracker is a little bit more tuned to high altitude ballooning. It does in-flight path prediction and landing spot prediction, as well as having links to SSDV if you want to see the pictures for the flight, and high split for floater flights. So this low power type transmitter really led to a number of small developments, physically small developments. People became interested in what became known as picohabbing, which was essentially to build a balloon and payload that fit within the UK 2-metre rule and thus didn't need a permit to launch. It became a natural development from this small size and power as a result of the limitations of not being able to use your amateur radio license. This is a full tracker made out of a couple of off-the-shelf components. It can be powered from anything from 2 volts to 3.5 volts, so fairly wide range of voltages. It's capable of transmitting LoRa, LoRaWAN, or FSK, or even MFSK. SSDV was developed by Phil Heron over in Northern Ireland. What it does is it takes in a JPEG file and breaks it up into a number of packets, but in such a way that if one or more of the packets are lost, the entire image isn't. It's equivalent really to a digital or packetized digital version of slow scan TV, but it's got some subtle differences. Because of our listener network, the packets can be received by multiple stations. They're all fed to a single point, and so the overall number of packets that are lost is less. If a packet is lost, then it's in-filled on screen with an appropriate colour. But if you've got a backward channel, you can also request that packet to be resent and the picture corrected. This is a real-time screen recording of SSDV working. In this example, we're using 1280 by 960 pictures, but you could use a different size if you wanted to. The smaller the picture, the quicker they come through. On the left-hand side, about halfway down, you'll notice that the packet has been missed, and as a result, it's been infilled with an appropriate colour. What happens now is the ground station can request that packet to be resent and infilled with the appropriate pixels, so completing the picture. Pie in the Sky is a development by a couple of British amateurs, Dave and Anthony. Here's a quick picture of them. Dave is on the right and Anthony on the left. Dave is responsible for the software, and Anthony looks after the design of the hardware. Basically, these are some add-ons to the Raspberry Pi computer that allow you to do tracking and slow scan TV and a number of other things. In fact, it's quite a considerable body of work that Dave has done here that allows you to do quite a number of different jobs on the Raspberry Pi whilst in flight, and also supports quite a number of different sensors and things that you can plug in. The Pie in the Sky comes as either you can buy a number of modules that plug in, or you can make your own, and it's all open source, and the design is out there, so you can either choose to purchase the boards, or you can put something together yourself. And an example there on the right hand side is a tracker I made, just GPS and an LoRa module and a camera, and that gives you the basic tracking and SSDV capability. Raspberry Pi itself is a single board computer based on an ARM processor, runs at about a gigahertz, and has about half a gig of memory. GPU can have HDMI output if you plug it in, and is running an operating system that's Linux. So together with a few other bits and pieces such as SD card and GPS, you can put together a working high altitude balloon pie in the sky for around about $25. This sped up screen recording is a demonstration of the ARHAB tracker displaying landing spot prediction, and also the Raspberry Pi calculating that landing spot using a completely different method. The Raspberry Pi is calculating the landing spot based on the ascent wind profile that it captured during the ascent. The red cross is the Raspberry Pi's estimate of the landing spot, and the blue line and blue dot is the ARHAB tracker's estimate. There is some variation here, and that's caused by changing descent rate. Essentially, a lot of that's caused by GPS noise, but you can see that the Raspberry Pi is making a pretty good job of working out where it thinks it's going to land. I'll leave that there, but it's a pretty good demonstration of the capability of the Raspberry Pi to do reasonably complex compute jobs, at the same time as doing everything else. We've been using LoRa as a modulation technique for ARHAB for about 5 or 6 years. It's actually grown to the point now where it's coming to be the dominant way that we use for transmission. It stands for long range, and it's a protocol and modulation technique that's been designed primarily aimed at low data rates and long distance. It's sort of the opposite of going faster and faster. It's in fact looking at how far you can get with the transmissions. It's an interesting chirp spread spectrum technique, which I'll come on to in a little bit more detail in a minute. But it allows data rates up to about 37 kilobits per second. I think actually now the newest chips go up to about 56. What you get is a full dual band data transceiver on a chip. So the chip shown there is about 1/4 inch across. The latest set of chips actually do range measurement as well. So they measure the ping time, the round trip time, quite accurately. And I guess it'd be possible to do away with the GPS by having some fixed locations and measuring the ping times from each of them. So that'd be quite an interesting alternative to GPS. Coming on to the detail of chirp spread spectrum, CSS uses a series of frequency sweeps called chirps. The chirps rack around in frequency for each symbol. A packet of data starts with a number of ascending frequency chirps, followed by a couple of downward chirps, which give the frame synchronization. Then the data is carried in chirps that vary their start frequency, the amount of frequency jump conveying a number of bits of data at the same time. I get the impression that this sort of continuous sweeping provides a protocol with a bit more immunity to things like static interference on the same frequency. Anyway, a number of data techniques are used to achieve a pretty impressive overall performance. It's at least as good as any of the other modulation techniques I've used. They claim up to 168 dB link budget, which seems reasonably well suited to low power. I mean, if you've got low power, you need a lot of link budget. And the crowded sort of license exempt bands have a lot of noise on them, so hopefully anything that can overcome that is good. So you can make a what we call a gateway, a Raspberry Pi and a LoRa receiver for as little as about $10. So it's really comparable with SDR. The claim is that this protocol is more resilient to noise and multipath and Doppler effect. I imagine primarily because of the chirp spread spectrum technique. LoRaWAN is a wide area network that's been layered on top of the LoRa physical layer. It supports the Internet of Things. In essence, it allows millions of devices potentially to connect back through the Internet to applications that the consumer or companies that own these devices might be interested in. It uses the license exempt bands, and typically the allocation is different in each of the countries. Obviously, due to being in license exempt is low power and also low duty cycle. So you won't be transmitting huge amounts of data this way. It's really only suitable for short bursts of data. It is bidirectional, so you can send data to your device as well as receive data from it. So the Things Network is a network provider that uses the LoRaWAN devices to provide a global network. The software on it is open source and the service is free. It's provided by people with an interest in obtaining data for their device, but also by doing so providing the infrastructure for other people to use in that same area. It's quite an interesting model, really. Here's a map of the current coverage worldwide. You can see there's a huge concentrations of nodes in the UK and Europe, in several thousand, and across the globe, still a fair density of nodes too. I'm wondering whether this is in fact quite useful for as an alternative to say APRS or HF or Pico balloons that fly around the world. So I've got some interest at the moment in seeing whether or not I can get a Pico balloon to use LoRaWAN to get its data back and potentially communicate with it via the LoRaWAN, rather the TTN network. I thought I'd wrap up with a couple of slides about the impact of high altitude ballooning on UK ham radio. When we started high altitude ballooning in the UK, the first wave of hammers became interested in amateur radio as a result of doing high altitude ballooning. Many of them I don't think had even thought of that before, but as a result of seeing how useful radio was for tracking, they went on and became interested in amateur radio in its own right. The majority of UK habbers now are amateur radio enthusiasts, at least the circle that I rub shoulders with. I think that's as a result of people being drawn in by the listener network. Having been involved maybe in hearing a few flights on 77s, they've been drawn into the hobby. So I think that's probably something that's more to do with the technical nature of the hobby and both high altitude ballooning and amateur radio. So is there a possibility of getting the UK license changed? I don't think so. We did some testing way back that gave Ofcom some ammunition. Some of the equipment that we tested, standard amateur radio equipment, didn't handle cold temperatures very well, and that just gave them more of an argument to not let us fly our amateur radio kit on high altitude balloons. And there was a review of the license as a result of Ofcom wanting to grab some frequencies back, I think. And while that looked hopeful initially, what actually happened at the end of that was more words were inserted into the license that makes it very clear that you cannot fly a balloon with amateur radio equipment in. So we're no further forward. In fact, I think we're further back. So I don't think there's any likelihood of this changing in the near future.
Quick question. You mentioned you wanted to do raccoons. I've done several. One was with a 400-pound rocket in the Gulf of Mexico, and I sent you a link of our igniting it in the stratosphere.
I've read about that bit in the past, actually. yeah. I knew you'd done one. Pretty several. Good on you. It's the regulation here for doing a raccoon is
months of paperwork, and we had to deal with dozens of government agencies, and we had to be 200 miles off the coast of the mainland to launch it. So we had to go out in a large, expensive boat. The advantage was that we could knock the wind speed to zero by putting a pilot balloon in front of the wheelhouse. And we inflated this 500,000 cubic foot balloon from Raven just beautifully. It just went straight up, zero wind speed.
Yeah, I was really just like after doing something
it cost $3,000.
Even a bit more humble. We've been looking at launching something like a K power rocket from a balloon. I think we can just touch space with that. So,
well, we figured it would reach 100 kilometers with the one we flew that was 400 pounds, but unfortunately the rocket engine separated at liftoff, so it just lifted up slowly under nitrous pressure. So, but we did have one go up to 36 kilometers.
Right.
So we talked to Van Allen directly years ago, and he launched
the master.
Quite a few from boats. He launched quite a few from boats with different government and with the Navy and I forget who else, but he went out in a number of boats and launched his, and he got like 4,000 mile range altitude on some of his raccoons. But we did talk to him before he died, and he was a great resource. So I've been looking into this for many years.
Yeah, it's great. I mean, but it's, you know, the range that you need in order to launch it's got to be huge. The Gulf of Mexico would be good. Yeah, the
Right.
North Sea's too small, I think. So yeah. Okay, cool. Has anybody got any questions on, you know, say LoRaWAN?
Yeah, there were a few questions in the chat. If I could go back, actually, has anyone in the U.S. tried LoRaWAN? I guess you can't help with that one.
Nope.
Also, any of the LoRa radios able to switch frequencies as it changes regions?
Not that I'm aware. None of the commercial ones. I mean, you can certainly program them to do that, and that's actually part of what I'm currently working on. So yeah, you need some form of geofencing to get it to switch frequencies as it goes around the world. But it's all pretty well defined. I think probably what I will do is, once I get that working, is ship the module off to somebody in each of the areas just to make sure it works, because leaving it to an actual balloon flight to test that type of thing is going to be too bad. But yeah.
I was interested in that, Steve, and that was my big question, whether we can, we have a geofencing algorithm that Mike and Alan, W7QL, came up with a, actually, Mike, you came up with the integer-based point and poly algorithm, didn't you? But
yeah, I need to get that on GitHub one of these days.
Yeah, and we basically use that to switch APRS frequencies as we go around the world in the pico balloons.
Okay.
So that would be great to use for the LoRa. Can it go to all the can the one module go to all the worldwide frequencies?
Yeah, more or less. There's one of the modules I've got is by Microchip, and that's got some filtering in it. I'm pretty sure that although there's filtering in there, it's not going to worry the difference between 868 and 900 megs. You know, so I think one module will probably at least do all of the higher bands. There are a couple of allocations of LoRa that are lower in frequency, but I don't think actually they're probably not worthwhile using for around the world. So yeah. I mean, as far as geofencing goes, I've been using it for a long time. When we first started high altitude ballooning in the UK, we didn't have the predictor, so you needed something to chop your balloon down if it started to approach the coast here. So yeah, I mean that ran on a on a PIC microchip, sort of very low power thing. So you can run geofencing even with some fairly low power devices.
We use it, Steve, to make sure we don't transmit our pico balloons over the UK, Yemen, North Korea. You're right up there with all the North Korea and Yemen.
Yeah. It's strange, isn't it? I mean, I don't really know why the UK doesn't allow it. I've never had a really good explanation from our regulator. They're just very cautious. As I said in my presentation, I get the feeling that the air regulators had some input into this, and they're the real driver behind it, and our radio regulator is just scared of them. So that's probably the reason for it. Like I say, you can go and do it in Germany, you can go and do it in France, so why can't you do it in the UK? Don't know. But I got to say that I think it's been a driver to development. So it's a bit like I put right at the beginning, it's necessity is the mother of invention. You know, we've had to take in that limitation and try to work around it. And as a result, we've gone down a slightly different path to everybody. And as a result of that, you know, we've innovated a bit here and there. So
comment in the chat from Dave Ackerman that the LoRa modules are cheap and small and light enough that you could have one for each band. But that, as you said, probably the 68 and 915 megahertz are close enough to each other that the signal strength
Yeah,
matter much during switching. But certainly,
yeah.
looking at
Well,
the data
most
sheet,
of
the 433s certainly have a low pass filter, and that might
yeah.
not work in 900.
Certainly the LoRaWANs all tend to be up on the higher frequencies because they use a slightly wider sped spectrum band. So so I think you can do it on a single module.
I have a
And in
question.
fact, that little picture I put up halfway through of the 3.5 gram tracker, that's a complete LoRaWAN system, and it's got. In fact, that will actually support 2 bands. That's got 2 outputs on the module, one for low band and one for high band. So you could do 434 on one antenna and 868 on another.
Mike,
And
so for the data position data you're actually exchanging, is that APRS formatted, or did you devise your own format for the location exchange?
No, that's all our own format, really. I think some of that is like steeped in history, really. We started out doing this as just an experiment, and then because it worked, people jumped on it, and things were set in concrete. So our position strings are literally just a text string with latitude and longitude. You could read them yourself, manually. They're not very efficient, but it works. And it had some advantages in the early days when people started to do this. We didn't have a network to come back onto a map. So people would even receive it on their FLDigi and cut and paste the string into an email and send it to you, and you could read it. So it was quite good from that sense. But yeah, it's worked well really over the years.
So on the LoRaWAN, what kind of bandwidth can you use?
Well, it's sometimes it's actually quite quite wide bandwidth. It spreads the transmission over a wideish band, 128k kilohertz, but for very short periods of time. So it's a very little. When it's that wide, it's sending a very short packet. The narrower you make it, the longer it takes, obviously, to send the same message. And LoRaWAN does tend to be just.
I was thinking more of the
messages.
Yeah, the LoRaWAN limitations, like the things network. Does it have a bandwidth limit that allow you to use?
I mean, you wouldn't be sending images via it. I mean, it's literally just like a position string once every few minutes, or 30 seconds. Maybe that's probably as fast as you could do on LoRaWAN.
So once a minute, 100 characters or so, kind of limitation.
Yeah, you can do that. Maybe even as fast as say 15 seconds, but you'd really have to be using the widest rate, the quickest rate to send that at that peak. I mean, the limitations are. I mean, there's a regulatory limitation of 1% duty cycle, so 1% occupancy of the channel, and there's a LoRaWAN limitation of 36 seconds airtime a day, and that is. So that gives you an idea about how quick you want to make the packets. They can be in milliseconds.
36 seconds a day, okay.
36 seconds a day. That's the theoretical limit. Not a lot of people seem to take a huge deal of notice about that. But yeah, that's what you should be. For LoRaWAN, that's what you should be sticking to. Yeah. I mean, LoRa is different. LoRa is the modulation technique used by LoRaWAN. And with LoRa, you can do whatever you're allowed to within the limits of a license exempt operation. And I mean, some of the allocations we've got in the UK allow us to do continuous transmission, but at very low power. So I think that one is 5 milliwatts. So you can do continuous 5 milliwatts LoRa at 250 kilohertz wide. And that's what we use for the SSDV pictures that you saw coming through. It takes about 35 seconds to send a 1280 by 960 picture. So yeah, reasonably respectable. And the distance there, I've had something like 50 miles antenna to antenna, and those are just like dipoles using that 10 milli, oh no, yeah, 5 milliwatts LoRa. How are we doing? Any other questions?
Steve, what's the power output on LoRaWAN?
So it varies from country to country. I'm not sure in the US, but it's typically in the milliwatts. I mean, in the UK, the 868 band is limited to 25 milliwatts, I think. You may find in the US it's slightly higher. I think in general, the US seems to have higher power limits for license exempt operation. I think you guys can do almost a watt on Wi-Fi. Over here, it's something like I think it's 250 milliwatts for Wi-Fi. So it varies, but for LoRaWAN, you're probably talking, no more than about 50 milliwatts.
Actually, I think it is a watt because I use the 9Extend Digi links, and they're about a watt.
Right.
And I get pretty good range.
Well, you may find that a lot of the LoRa modules don't actually do that sort of power, but it would be worth. I mean, I could investigate for you if you like, but it's something that's a US specific thing, and in Australia it will be different again. So you've got to make something if you want it to go worldwide. You've got to make something that knows where it is and the limitations for that area.